Hello students, welcome to Grade 12 Mathematics Unit 4, which is Introduction to Linear Programming. Linear programming is one of very interesting unit which has so many applications to solve real life problems. So under this linear programming problem, we'll try to cover the following points. So we'll try to cover Introduction to Linear Programming. We'll try to see some terminologies related to linear programming. Then finally, we'll try to focus how to determine a maximum and the minimum value of a given objective function under given constraints. So here we have a terminologies. What is optimization problem? A problem which seeks to maximize or minimize a linear function which is called objective function, subject to a certain constraints determined by a set of linear inequalities. So this is optimization problem. And what's linear programming? It's a problem of finding a maximum or a minimum value of a given linear expression under given constraints. So what's objective function? The objective of linear programming is to find a maximum or minimum value of objective function. So objective function is a mathematical expression that defines what we want to maximize or what we want to minimize. So in general, objective function is a function that we need to find the optimal value. So this optimal value or a maximum or minimum value of a given objective function is determined by a linear constraints. So linear constraints are conditions that the decision variables must satisfy. Linear constraints are inequalities or equalities where each term is either a constant or constant times a variable. And also in linear programming there is a term which is feasible region. A feasible region is a set of all points in xy plane that satisfies all given constraints, including non-negativity constraints like x and y must be greater than or equal to 0. And what is optimal solution? Optimal solution is any point in the feasible region that gives optimal value of a given function. Optimal value is either a maximum or a minimum value of a given objective function. So generally, the objective of this lesson is to determine the optimal solution of a given linear programming. So optimal solution is any point in the feasible region that gives optimal value. Most of the time, this optimal solution exists at any corner points of a given feasible region. If optimal solution exists, it usually occurs at a corner points of a feasible solution, or it may be on a boundary line. If the optimal solution exists, the solution may be one unique solution, a single optimal point, or multiple optimal solution. It may be a whole edge and also no optimal solution. A given linear programming may have no optimal solution if the feasible region is either empty or if it is unbounded in the direction of optimization. If it is bounded feasible region, so it must have an optimal solution. If it is bounded, then a given linear programming problem will have both a maximum and minimum value. So how we can find the optimal solution of a linear programming? Finding the optimal solution is evaluating objective function at each vertex of a feasible region and choose the vertex that gives the best value, that is either a maximum or a minimum value depending on the given function. If it is to find a minimum value, we'll choose a point that gives minimum value from given vertices. And if the function is about maximizing, we'll choose a point that maximizes objective function. Now let's see how to find the optimal value or optimal solution. Solve a linear programming problem below by corner point method, or we call it graphically. We'll try to solve such types of linear programming using graphs. So maximize z, which is to x plus y. This is what we call objective function. This objective function, this is objective function, which is subjected to these linear inequalities. What we call these linear inequalities are constraints. So to solve this linear programming, we'll solve using corner method or we'll solve using graphical method. So which one should be drawn to find the solution? To find a maximum value of z, that's to x plus y, we'll draw a graphs of a constraints in one coordinate plane. So let's see how to solve using graphs. Here, now to solve a given linear programming, let's try to draw all constraints in one coordinate plane. The first one is graph of 3x plus 4y less than or equal to 12. And the second graph is a graph of 3x plus y less than or equal to 6. So, both graphs are shaded downward depending on a given linear inequality. And also, x must be greater than or equal to 0. X equals to 0 is a vertical line, that is the y-axis. So x greater than 0 is to the right of a y-axis. And also y equals to 0 is the horizontal line, that's x-axis. So y greater than or equal to 0 is a region which is above the x-axis. So after we draw these all linear constraints, which one is a common region? A common region implies when we draw all constraints in one coordinate plane, the region that satisfies all constraints is what we call a feasible region, which satisfies all constraints, This one is the graph of 3x plus 4y less than or equal to 12. This one is a graph of 3x plus y less than or equal to 6. And also there is a line which is y greater than or equal to 0. The horizontal line or the x-axis. Therefore, this is the region which is enclosed by all linear constraints. This one is also a line that is x greater than or equal to 0. So if this is a feasible region, the optimal solution will be obtained at one of a corner points. So we have here 4 corner points. So the optimal solution is obtained at one of these corner points. So how we can find these corner points now? This one is 0, 3. It's y-intercept of this line. And this is 0, 3. And we have this, which is 2, 0. And how we can find this point of intersection? It's a point of intersection of 2 lines. So this point is a point of intersection of 3x plus y equals to 12. This is linear equation, the graph of a straight line. And also 3x plus 4y equals to 12. Now we have 2 linear equations. Now we can solve these linear equations. We can solve by subtracting. These are a system of linear equation. So 3x minus 3x is 0, y minus 4y is minus 3y equals to minus 6. If we divide both sides by minus 3, y equals to 2. Then if we have a value of y, we can find the value of x. We can substitute y equals to 1 in one of the equations. 3x plus 2 equals to 6. So 3x equals to 6 minus 2. So 3x equals to 4. So x equals to 4 over 3. So this point of intersection of two lines is 4 over 3, then comma 2. So finding optimal solution for a given linear optimization is evaluating objective function at each of a corner points. If it is a maximizing problem, we'll identify which corner point gives a maximum value. If it is minimizing problem, we'll find which corner point will give minimum value for an objective function. Now let's evaluate an objective function for each of these vertices. Each of these vertices, or what we call each of corner points of a given feasible region. The region that satisfies every constraint. Here, any point on the feasible region will satisfy each of the constraints. Now, we have a corner points. The one is 0, 0. The other is 0, 3, 2, 0, and 4 over 3, 2. What is the objective function? It is z equals to 2x plus y. So we'll evaluate the objective function at each of the corner points. That's 2 times 0 plus 0 is 0. Twice of 0 plus 3, this one is 3. And z equals to twice of 2 plus 0, that's 4. And finally, z equals to twice of 4 over 3 plus 2, which is 14 over 3. What is the objective of this linear programming? The objective of this linear programming is finding a maximum value. Then after we evaluate each of the pointers, we'll identify which one is a maximum. From these values, we'll identify which one is a maximum value. So 14 over 3 is a maximum value. So since the objective of a given function is maximizing, z maximum equals to 14 over 3. And also, we can also state what is the minimum value. The minimum value of objective function, that is z minimum equals to 0. So, what is the optimal solution? The optimal solution is 14 over 3. What is the optimal point? The optimal point is a point that gives a maximum value. 4 over 3, 2 is optimal value. Then another example 2. This is a word problem, so we can apply linear programming to solve so many daily life problems. So furniture company makes a chair and a table. Each chair requires 1 hour for carpentry and 1 hour of painting. When this furniture company makes a chair and a table, each chair requires 1 hour for carpentry and 1 hour for painting. And each table requires 1 hour for carpentry and 2 hours for painting. And the company has at most 4 hours for carpentry and at most 5 hours for painting, time available each day. Each chair earns a profit of $3 and each table earns a profit of $2. So here, this furniture company has 2 constraints. It's about time constraint. The one is for carpentry, the other is for painting. And also, when this furniture company makes a profit, $3 for each chair and $2 for each table. So how many chairs and tables should the company make to have a maximum profit? Now, let X represents a number of chairs and Y be a number of tables. And also, what is the objective of this linear programming? Look, the objective of this linear programming is to make a maximum profit. So how we can write the objective function? How we can write the objective function? When the company prepares a chair, from each chair the company can make a profit of $3, and from each table the company can make a profit of $2. So the total profit that the company can make in a given day equals to 3 times the number of chairs, then plus 2 times the number of tables. So the objective function is Z maximum equals to 3x, that is 3 times the number of chairs, plus 2 times y, where y is the number of tables. Y is the number of tables. And also, the company has a time constraint. One for carpentry, the other is for assembly. So when a company makes a chair, each chair requires 1 hour for carpentry and 1 hour for painting. And similarly, when a company makes a table, it needs 1 hour for carpentry and 2 hours for painting. And also, the company has at most 4 hours for carpentry. So, the first constraint, x plus y must be less than or equal to 4. This is time constraint for carpentry. X is a number of chairs plus a number of tables must be less than or equal to 4. This is a time which is easy to make, x number of chairs and y number of tables for carpentry. And also, each chair requires 1 hour for painting and each table requires 2 hours for painting. That's 2y. The time required to paint a number of y tables is 2y. This must be less than or equal to 5 because the company has a time limitation which is 5 hours. And x must be greater than or equal to 0 because it represents a number of chairs, and y must be greater than or equal to 0. These are what we call a constraints. And what is the objective function? It is 3x plus y, which subject is to x plus y less than or equal to 4, x plus 2y less than or equal to 5, x must be greater than or equal to 0, y must be greater than or equal to 0. So how we can find the maximum value of this objective function? So we'll draw to find a maximum value of a given objective function. So let's draw the graph. Here we can draw, we have this coordinate system. So we have a constraint is 1, x plus y less than or equal to 4, and x plus 2y less than or equal to 5, x greater than or equal to 0, y greater than or equal to 0, and the objective function is z, which is 3x plus 2y. So finding a maximum value is, we'll draw first a graph of these linear constraints. So to draw graph of x plus y less than or equal to 4, to draw graph of x plus y less than or equal to 4. So we'll find first the graph of x plus y equals to 4. Let's find a graph of x plus y equals to 4. So to draw graph of a linear function, it's better to consider x and y intercept. When x equals to 0, y is equal to 4. So let's locate roughly 4 and y 0. When y equals to 0, x is also equals to 4. Let's say this is x, which is 4. Then we'll connect these 2 points by a smooth line. So after we draw this straight line, a feasible region is either downward or above from this straight line. So how we can choose that? So from the original linear inequality, we can substitute any test point to determine the feasible region. Now, x plus y less than or equal to 4. Let's take one test point. Let's take a point which is 0, 0. And let's test whether it makes this linear inequality true or not. 0 plus 0 less than or equal to 4. So it is true. If it is true, the graph of the region is to the side of the point. So the feasible region is a downward. And similarly, we'll draw a graph of x plus 2y less than or equal to 5. So let's draw similarly. So we'll consider x plus y equals to 5, which is linear equation. At x equals to 0, y equals to 5 over 2. 5 over 2. 5 over 2, 2.5. So this is 5 over 2. And when y equals to 0, then x equals to 5. If we substitute y equals to 0, x must be equal to 5. So let this one is a 0.5. So if we connect these points by straight line, similar to the previous one, we'll find the region either downward or upward. Let's take a test point 0, 0 and let's substitute on a given linear inequality. So if we substitute 0, 0 plus twice of 0, which is less than or equal to 5. That is 0 less than or equal to 5. This is also true. So we'll shade downward again. Downward. And also, finally, x greater than or equal to 0 is to the right of a y-axis, and y greater than or equal to 0 is above the x-axis. So when we draw all these constraints, which one is a feasible region? A feasible region is this region, which is enclosed by all of the constraints. Always the feasible region in this case is on the first quadrant, So after we determine now the feasible region, we'll try to determine every corner points. So here we have 4 corner points, 1, 2, 3, 4. So the one is 0, 0, that's a corner point. Then the other one, 4, 0. Then the other point or the other corner point is 0, 5 over 2. And we have another corner point. How we can find this corner point? This point is a point of intersection of these two linear equations. So we have these two linear equations. X plus 2y equals to 5 and x plus y equals to 4. So to find this point, let's subtract this minus y equals to minus 1. So y equals to 1. If y equals to 1, what is the value of x? If we substitute 1 in place of y, x plus 1 equals to 4. So x must be equal to 3. So this point of intersection is 3, 1. So after we find all these corner points, all these corner points. After we evaluate every corner points, we'll evaluate objective function z. The objective function z equals to, it is 3x plus 2y. 3x plus 2y. So finding the objective, a maximum value implies we'll evaluate z at each point. So z equals to 3 times 0 plus 2 times 0. It's equal to 0. X and y equals to 0, meaning a number of chair and a number of table 0, 0. There is no production and there is no profit. So z at 4, 0 implies x represents a number of chairs and y represents a number of tables. 3 times 4 plus 2 times 0. This value is equal to 12. When a company makes 4 chairs and 0 table, the company can make a profit of $12. And the other value, when 0,5 over 2, 3 times 0, then plus 2 times 5 over 2. This one is equal to 5. When a company makes 0 and 5 over 2, z is equal to 5. And finally, z equals to 3 times 3 plus 2 times 1. That is 9 plus 2, which is 11. Now, the problem of this linear programming is finding a maximum value or a profit. It's making a maximum profit. So we have this maximum value. So what is z maximum? Z maximum equals to 12. So company can make $12 only by making 4 chairs. So in general, to find the optimal value of a given linear programming, we'll draw all linear inequalities on one coordinate plane. We'll identify the feasible region. That's a common region for every linear inequalities. After that, we'll try to determine every corner point. After we determine every corner points, evaluate objective function at each of these corner points. Then, if the problem is a maximizing problem, identify which one is maximum. If the problem is minimizing problem, identify which one is minimum value of a given objective function. So here, for this problem, the maximum value is 12. And what is the optimal point is 4, 0. So this one is exercise for you. Solve linear programming problem given below by corner method, meaning by using graph z equals to 8x minus 2y subjects to 3x plus 2y less than or equal to 12 and x minus 2y less than or equal to 2, x greater than or equal to 0, y greater than or equal to 0. So follow the procedure, draw these constraints, identify the feasible region, find all corner points and evaluate z at each of the corner points. Then after you evaluate, pick the minimum value of objective function. So the minimum value is minus 12. Do and check the answer. Solve linear programming problem below by corner point method. Minimum value of z. Z is 8x minus 2y subjects to 3x plus 2y less than or equal to 12 and x minus 2y less than or equal to 2, x greater than or equal to 0, y greater than or equal to 0. So what is the procedure? Draw a graph of constraints on a coordinate system, then identify the feasible region, the common region for every linear constraints. Then find each of corner points of that feasible region and evaluate Z at each of a corner points. Since the problem is minimizing problem, pick a minimum value of Z. So do and check, the answer is minus 12. Example 2, it is the same problem. Solve a linear programming problem below by corner point method. Draw these all constraints on a given coordinate system, on single coordinate system. Then identify the feasible region and find every corner points. Then evaluate Z at each of a corner points. And finally, identify which one is the minimum value from each of a corner points. So in general, from the lesson we have seen this optimization problem, a problem which seeks to maximize or minimize linear function subject to certain constraints. And we have seen how to determine optimal solution, either a maximum or minimum value of a given objective function if it exists. So the solution of optimal solution for linear programming exists. If it exists, it is usually occurred at a vertex or corner points of a feasible region, or it may also exist along boundary lines. So this is all about the lesson. See you next time.